Why do Earth days continually vary in length? We are all aware that an Earth day is, in fact, made up of 86,400 seconds. This has been understood since Muslim scholars split the average solar day into 24 hours and the associated minutes and seconds in the year 1000. However, as soon as our instruments improved, we found that the Earth's rotation period varied erratically by about a second per year. Later in this video, we shall learn how it is feasible, but for the time being, consider what would happen if our clocks were only a few seconds off. Those few seconds can add up over time and result in significant inconsistencies in timekeeping. To ensure that our clocks are as accurate as possible, scientists had to define the term leap second. To put it into perspective, consider how much smaller a leap second is than a leap year. In order to account for the fact that the Earth's orbit around the Sun is not precisely 365 days long, a leap year is added every 4 years. Therefore, to adjust for the minute changes in the Earth's rotation, we add an extra second to our clocks as necessary, just as we do every 4 years when we add an extra day to February. Considering that one only gets to celebrate their actual birthday once every 4 years, some people might believe that being born on a leap year is unlucky. However, let's face it, they age 4 times more slowly than the rest of us, so perhaps it's not so bad after all. But jokes aside, the Earth's slowing rotation is a genuine phenomenon with significant effects on our planet's climate, geography, and even timekeeping. So let's examine the science behind it all and find out what is causing our planet's rotational speed to change over time. Leap second. The definition of a leap second is important for maintaining precise time on Earth because it aids in synchronizing atomic time with the planet's rotation. All of this is very significant because, well, you don't want to be even a single second late for your NASA job interview. Only 6 months in advance are leap seconds announced due to the unpredictable and erratic changes in the Earth's rotation speed. The mathematical model created by physicists Stephenson and Morrison depicts a constant lengthening of the mean solar day of 1.70 milliseconds per century. However, over the past few centuries, the sum of the periodic component and the overall rate has been about 1.4 milliseconds per century. The model makes one thing abundantly clear: the Earth is slowing down. Yet why? How is it even conceivable that tidal friction, which lengthens the day by 2.3 milliseconds every century, is the main cause of the Earth's rotation slowing down? The movement of the Earth's crust in relation to its core, variations in mantle convection, and any other occurrences or processes that result in a large redistribution of mass are further contributing variables. Due to the conservation of angular momentum, these processes change the Earth's moment of inertia, which has an impact on the rate of rotation. Some redistributions oppose tidal friction, shorten the solar day, and speed up the Earth's rotation. How does the moon slow the Earth down? Pay attention to tidal friction now, and how precisely does it cause the Earth to slow down by 2.3 milliseconds every century? When two objects, such as the Earth and the Moon, interact, tidal friction is created. The gravitational forces from the Moon cause tides in the oceans, causing them to rise and fall twice a day. As the tides move across the Earth's surface, they create friction which generates heat. This heat causes the Earth's rotation to slow down gradually over time. As the tides move across the Earth's surface, they rub against the land and create heat. This heat then causes the Earth's rotation to slow down. It can be challenging to understand how tidal friction works, so let me give you an example that you are likely to understand. If you've ever spun one of a bicycle's wheels while it was upside down, you may have noticed that placing your hand on the tire will cause it to spin more slowly. Tidal friction lengthens our days by acting as a brake on the Earth's rotation. Tidal friction is a natural process that is controlled by the rules of physics, not magic. It is significant to note that a number of variables, like the size, distance, and shape of the Earth, affect how much friction is produced by the tides. The existence of life on our planet and the understanding of the Earth's rotation both depend on this occurrence. The oceans on Earth would be stagnant without the tides produced by the Moon, and life as we know it might not have developed. The tides assist maintain the Earth's climate by giving marine life vital nutrients and oxygen. Tidal friction is not only produced by the Earth-Moon system. Our solar system's planets and moons are two more well-known examples. For instance, we are aware that tremendous tidal friction occurs on the moons of Jupiter and Saturn, which results in their having active volcanoes and geysers. How does the ice affect the rotation of the Earth? But it's not the end yet. The Earth occasionally enjoys accelerating its rotation as well. Let me give you an example, the end of the last ice age, which occurred 20.000 years ago. A redistribution of mass on the Earth's surface as a result of glacier and polar ice cap melting has an impact on the rotation of the planet. The water from the melting glaciers was moving towards the seas, affecting the mass distribution of the Earth and altering its moment of inertia. Our planet's overall rotation accelerated as a result of this change in moment of inertia. The loss of ice mass in Greenland and Antarctica has accelerated the rotation of the Earth, according to a study that appeared in the journal Science Advances. The Earth's axis has shifted, tilting further towards the east as a result of the melting of the ice in these places, the researchers discovered. The length of a day has decreased over the past century by around 1.8 milliseconds due to this change in the Earth's spinning speed. What's particularly intriguing is that we, as humans, have the ability to alter the Earth's rotational speed. And it's not always a wise way to go about doing that. Consider the ice melting due to climate change. Though the impact will be small, it can have a similar impact on how the Earth rotates. According to a study in the journal Science Advances, the Earth's rotation could quicken by about 12 microseconds annually as a result of glacier and ice cap melting brought on by climate change. Despite the fact that this effect is small, it could accumulate over time and significantly affect how long a day is in the future. How do earthquakes affect the Earth's rotation? Earthquakes can also alter the duration of the day on Earth, but in a different way. When an earthquake happens, it can induce a redistribution of mass on the Earth's surface. The Earth's moment of inertia is impacted by this shift in mass distribution, which has an impact on how quickly or slowly the Earth rotates. As an illustration, the magnitude 9.0 earthquake that devastated Japan in 2011 resulted in sufficient mass redistribution to shorten a day by roughly 1.8 microseconds, or roughly 1.8 millionths of a second. This is due to the earthquake's massive mass transfer from the equator to the poles, which caused the Earth to spin a little bit faster. But not every earthquake has this result. The amount of mass redistributed and the impact on the Earth's rotation depend on the size, location, and kind of the earthquake. In order to better understand how earthquakes can affect the rotation of our globe, scientists are still researching this issue. The world's shortest day. You may only have one major query left at this point. If the length of days on Earth varies arbitrarily, what is the shortest day ever observed? Indeed, this is a very good question. And the answer is, probably, it happened on June 29, 2022. The duration of that day was 1.6 milliseconds under 24 hours, making it the shortest day we know in history. This actually brings out something crucial. The Earth's shifting in rotation depends on a range of elements, and the random combination of some of them can have varying results on the duration of a day. It could make it at times shorter, at times longer. Will the shortened day mount up over a lengthy period of time? We might need to employ a negative leap second. Negative leap second. In fact, it is crucial to highlight that leap seconds are not signs of a slowing of the Earth's rotation rate. Instead, they are indicators of the accumulated disparity between atomic time and time measured by Earth's rotation. The average length of the day in 1972 was around 86,400.003 seconds, whereas in 2016, it was roughly 86,400.001 seconds, demonstrating an overall rise in Earth's rotation rate over that time period. Positive leap seconds were added during that time because the annual average length of the day remained greater than 86,400 International System seconds, not because of any slowing of Earth's rotation rate. Recent reports show that Earth was spinning faster in 2020 and experienced the 28 shortest days since 1960, each lasting less than 86,399.999 seconds. That's what led engineers worldwide to discuss a negative leap second and other possible timekeeping measures that could eliminate leap seconds. This, in turn, underscores the significance of precisely defining a leap second to ensure the precision of timekeeping on Earth. Here's where the video ends. What do you think about the Earth's rotation changing? Tell us in the comments section below, and see you on the channel again soon.